Hello everyone and welcome to the coronavirus edition of the sixth lecture from our signal theory class. Today we will start talking about continuous time systems and how we can describe them with a differential equation. Previously we had discrete systems and those were described using the difference equation. The difference equation gave us a relationship between the input and the output in the time domain. For continuous time systems, we need something similar, and it will be so-called differential equation. To explain the description of continuous time systems with a differential equation, I will use some mechanical examples which are easy to understand intuitively, so hopefully it will be easy to see how the math is connected to the real world. Here I have a simple example where my continuous time system is a car and I want to describe its movement. In fact, I will be only interested in the velocity of this car, which I will denote by this vector. I will also consider that there is some force acting on this car, and that I will denote with this vector. The force acting on the car can be typically composed of two components. One component is the force generated by the engine, and the other component is the resistive force acting against the movement of this car. Normally, this could include various kinds of friction and air resistance. In this example, I will assume that the engine of the car is off and that the car is coasting, so this force is zero. I will also assume that the resistive force can be simply approximated and expressed as proportional to the speed of the car. The faster the car goes, the more resistance it encounters. This C would be some coefficient of friction. Now, to describe the movement of the car, I need to use the simple equations of motion. By Newton's law, the acceleration is given as the force divided by the mass of the car, and when I substitute for this force, I get this. Now, the derivative of the velocity is acceleration, and when I substitute acceleration here, I get this. In this equation, I will put all the terms with speed to the left-hand side, and that gives me this equation. This is so-called differential equation. It is an equation that describes properties of a function, in this case our velocity, and to solve this differential equation we need to find this function so that it will satisfy this entire differential equation. An equation like this is called the first order ordinary differential equation with constant coefficients. That first order comes from the fact that the highest derivative is the first derivative. If the highest derivative was 5, then we would have fifth order differential equation. The name ordinary comes from the fact that we are differentiating with respect to a single variable, in this case time. If we had derivatives with respect to more variables, we would call this a partial differential equation. Last, those constant coefficients refer to these constants which multiply our function and its derivatives. In general, these do not have to be just constants, but if your function and its derivative are just multiplied by some constants and summed together, we talked about ordinary differential equation with constant coefficients. When we put the terms with our unknown function and its derivatives to the left-hand side and we are left with 0 on the right-hand side, we say that this equation and this system are homogeneous. Actually, if the car's engine was generating some force, we would not have 0 here, and this force would appear here. In that case, this equation and this system would not be homogeneous. Typically, external sources of signal or energy that input our system appear on this right-hand side. So if the system is homogeneous, it typically means that there are no external active sources inputting the system, like that the engine of this car is off. Now let's take a look at how we can solve this equation. That means how we can find this function that describes the velocity of the car. Despite of what you might have heard or experienced, solving differential equations in many cases is very easy. The solution is already prepared for you and you just need to find some constants. And this is also our case. If you have an ordinary differential equation with constant coefficients, then you can expect the solution in this form. These a and lambda are just some constants, and all you need to do is to find them. How do you do that? Well, you take your differential equation and substitute this solution. Then you take this derivative and you get this. Here you need to observe that you can actually cancel this a and this exponential like this. When you do that, you are left with this equation, which is an equation for lambda. This equation for lambda we call the characteristic equation. When you solve it, you will get that the lambda is equal to minus c over m. This solution we call the root of the characteristic equation. Now, when we know what lambda is, we can substitute it into the solution we started with, and we get this. This is so-called general solution. You can see that I still have an unknown constant here. This constant can be anything, and with different values of this constant, I will get different functions. The thing is that all these different functions describe all possible ways how your system can behave. Therefore, we call this a general solution. It describes all possible ways how your system can behave. In fact, if you take this general solution and substitute it into the differential equation of our system, you will find that it fits for any constant a. Now, it is nice that we know all possible ways how our system can behave, but how can we find one specific way how our system is going to behave? This we need to get from so-called initial conditions. In addition to the differential equation itself, I need to say something about the initial state of our system at some initial time point. Often we use 0 as the initial time point. And only after I specify this initial condition, I can get that one specific behavior of my system. So here I have it specified. I say that at time 0, my car will have the initial velocity v0. With this initial condition, I can express this general solution at time 0. I have that here. Here I can see that this exponential is 1, and I'm left with a. And from the initial condition, the velocity at time 0 should be v0. That means that a is equal to v0. So now I can substitute this v0 into my general solution and I will get this. This is the specific way how the velocity of my car is going to behave for this initial condition. And we call this the particular solution. When I set some specific numbers, for example, I say that the initial velocity is 1 and the coefficient of friction divided by the mass of the car is 1, I will get this specific function of velocity. You can see that the initial velocity is 1 and the velocity exponentially slows down to 0, which is pretty much what you would expect from a car with engine turned off. Here I have a different example which is closer to the heart of an electrical engineer. This is an RC circuit. I have no sources in this circuit, but I will assume that at time 0 this capacitor is charged to some voltage V0. Now, how can I describe the behavior of the voltage in this circuit? Well, first I have to describe this system using a differential equation. From basic circuit theory, I should know that the current through the capacitor is proportional to the derivative of the voltage on the capacitor, with constant of proportionality equal to the capacitance. And from the Ohm's law, I get that on this resistor, this is the relationship between the current and the voltage. When I substituted the first equation to the second one, I get this. And when I put all the expressions containing my unknown function to the left-hand side, I get this. And this is an ordinary differential equation with constant coefficients. Also, you can see that this differential equation is homogeneous because this right-hand side is 0. This corresponds to the fact that there are no sources in the circuit. If you had some sources in the circuit, they would appear on this right-hand side and the differential equation would no longer be homogeneous. So, we can look for the solution in this form. We just need to find these constants a and lambda. I substitute this solution into my differential equation. I have that here. Evaluate the derivative, cancel the a's and exponentials, and I will get this equation for the lambda. This is the characteristic equation. When I solve it, I get this root of the characteristic equation. Now I substitute this value of lambda into my solution, and I get this. This is the general solution that describes all the possible ways how the voltage in this circuit can behave. But I'm not interested in all the ways how this circuit can behave. I'm interested only in the case where at time 0 this capacitor is charged to voltage V0. So I need to use this initial condition to find my particular solution. The initial condition is given at time 0, so I will evaluate my general solution at time 0, and I get this. This is supposed to be equal to V0. So the constant A is V0. I can substitute this into my general solution, and I arrive to this particular solution that gives me the time course of the voltage on my capacitor. Now to check the solution, I can set some specific values. For example, let's say that the initial voltage of the capacitor is 1 volt and the product of the resistance and capacitance is 1. In this case, I will get this voltage on my capacitor. You can see that the capacitor starts at 1 volt and then discharges exponentially to 0. This capacitor is discharging through this resistor and this voltage is dropping exponentially to 0. So based on the previous examples, you should start to understand how I solve a general homogeneous first order system described by an ordinary differential equation with constant coefficients. In general, the differential equation will look like this, and we specify some initial conditions like this. The solution can always be found in this form, and you just need to find these constants, A and lambda. To find these constants, you can substitute this solution into your differential equation, evaluate the derivatives, cancel out a's and the exponentials, and you will arrive to the equation for lambda, which is called the characteristic equation. You evaluate this equation and you get this solution, which we call the root of the characteristic equation. Now you can substitute this root into the original solution and you will get the general solution that describes all possible ways how your system can behave. Then, to find how your system is going to behave for this specific initial condition, you need to evaluate your general solution at time in which the initial condition is given. And from there you will find the value of the constant A. And finally, you substitute this value into your general solution, which will give you your particular solution. This particular solution describes how your system behaves for your initial condition. In general, we recognize two types of behavior of these first-order systems. The behavior depends on the value of lambda, that is on the value of the root of the characteristic equation. If lambda is negative, you will get this behavior where the system exponentially goes to 0 and stabilizes there. In this case, we say that the system is stable. Alternatively, if lambda is positive, you get behavior like this one. The system exponentially rises to infinity or minus infinity. In practice, this can mean that the system is going to explode or something. In this case, we say that the system is unstable. Okay, now let's take a look at something more complicated. Let's take a look at a second-order system. As with the first order system, I will start with a mechanical system that is easy to imagine and understand intuitively. My system will be a ball on a spring. I have this ball with mass m that is lying on this surface and it is attached to this surface with a spring with stiffness k. The position of the ball I will measure in this coordinate system and will denote it with y of t. Here I have indicated the direction I will use for the force acting on the ball. The force acting on the ball will have two components. The first component is the force generated by the spring. If you move the ball in one direction, the spring will create force in the opposite direction. Thus, this minus sign. The force will be proportional to the displacement of the ball, and the constant of proportionality is the stiffness of the spring. This force component is the friction. This is the same as with the car. It is proportional to the velocity of the ball, and the constant of proportionality is the coefficient of friction, which I have denoted here as C. Now, if I want to describe how this ball moves, I need to use equations of motion. The acceleration is given as the force divided by the mass, and when I substitute for the force from here, I get this. Next, the derivative of velocity is acceleration, and the derivative of position is velocity. When I substitute this equation here, I get this equation. And when I substitute for the acceleration from here, I get this. In this term, instead of velocity, I will use derivative of the position. Finally, I will put all the terms with my unknown function to the left-hand side, which will give me this equation. And again, you can see that this system can be described using an ordinary differential equation with constant coefficients. Moreover, this equation is homogeneous, which reflects the fact that there are no external forces acting on this system. To solve this differential equation, we will start as before, and we will expect the solution in this form, even though later I will show you that there is one case where you have to alter this form slightly. As before, we will substitute this solution into our differential equation, and we will get this. To solve this, we need to evaluate the derivatives, which gives us this. Here we can cancel out a's and exponentials, which as before gives us equation for lambda, except this time it is the second order polynomial. And as before, we refer to this equation as the characteristic equation. The next step would be solving this characteristic equation and finding lambda, but if I did this for a general case, the math would get ugly. Therefore, instead of working with some general c, m, and k, I will set some specific values and I will work with them. Moreover, I will do this in several variants, which will show you various possibilities how this system can behave. The first variant will be this. I will set the coefficient of friction to be 3, the stiffness of the spring will be 2, and the mass of the ball will be 1. In this case, the characteristic equation will look like this. To solve this equation, I need to find the discriminant, which is 1. And then I can find my lambdas like this, which will give me -2 and -1. Note that in this case, my discriminant is positive real, which gives me 2 real solutions for the lambda. Here, we have the first major difference from the first order system I showed you earlier. With the first order system, I got only one root of the characteristic equation, but with the second order system, I get 2 roots of the characteristic equation. But which one should I pick for this lambda? You actually use both. Your differential equation would be satisfied if you used only this first root and only this first exponential. And your differential equation would also be satisfied if you used only the second root and only this second exponential. But you can also check that if you make a sum of these two exponentials and substitute this solution into your differential equation, this combined solution will satisfy your differential equation as well. At this point, I'm looking for the general solution of my differential equation, that is the solution which will describe all possible behaviors of my system. So I'm looking for the most general case, which is the combination of both these exponentials. So this combination will be my general solution that describes all behavior of my system. Again, to get the particular solution, I need to find these constants a1 and a2. And those I will get from the initial conditions. So let's set some initial conditions. Let's set that at time 0, the position of my ball is 1. That means that at time 0, I have pulled this ball 1 meter to the right. To use this initial condition, I need to evaluate my general solution at time 0, which I have done here, and from this, I will get that the sum of a1 and a2 needs to be 1. You can see that this says something about a1 and a2, but it does not yet allow me to compute their specific values. Because this is the second order system, one initial condition is actually not enough to describe the initial state of the system. To fully describe the state of this system at some time, I need not only specify the position of the ball, but also the velocity of the ball. So I need to add the second initial condition. Let's say that in this example, the initial velocity, that is the derivative of the position at time 0, is 0. So my initial state of the ball is that it is displaced by 1 meter to the right, but otherwise it is not moving. Now let's use this initial condition. First, we need to express the derivative of the general solution, which I have done here. Then I need to substitute time 0, and that gives me this equation. And now I have two equations of two variables a1 and a2. I can solve this system of equations, which will give me this solution. These values I can substitute into my general solution, and that will give me this particular solution of my second order system. You can see that now the behavior of the system is described by the sum of two exponentials. When I plot them, I get this. The blue line is actually a separate plot of my first exponential, this first exponential, and the green line is a separate plot of my second exponential, this second exponential. When I add them up, I get this black line, which is the position of my ball. You can see that the ball starts at 1, as per this initial condition, and the initial derivative appears to be 0, as per this initial condition. And then you can see that the ball exponentially comes to rest at position 0. You actually get this type of behavior when the friction is sufficiently strong in comparison with the stiffness of the spring. If the friction is sufficient, the ball will just come from some initial position to the 0 position. Now let's take a look at what happens when I decrease the friction and increase the stiffness of the spring. Here I have friction coefficient 3 and stiffness 2. In this case, I have coefficient of friction only 2 and stiffness was increased to 10. Let's solve this case. Now the characteristic equation will look like this. The discriminant is negative, so the roots of this characteristic equation, which you can compute like this, will be two complex conjugate values. In general, I can denote such roots as sigma plus j omega and sigma minus j omega. Now the general solution will look like this. Formally it is the same as before, but now the roots of the characteristic equation are complex numbers and these are complex exponentials. It is possible to compute and find the particular solution using the general solution in this form, but those complex numbers make it really painful. A simpler way will get you the following trick. When I use this general form of roots of the characteristic equation, I can write the general solution like this. Now you can actually express the real and imaginary parts of these complex exponentials. And when you do, you will find that the imaginary parts will actually cancel each other out, and when you crunch the math, you will get this expression. Here, where I wrote C1 and C2, you would actually get some combination of these A1 and A2. But whatever comes here and here, I have just denoted as C1 and C2 and will work with these constants instead. So this is an alternative form in which you can write your general solution. There are two differences against this form. First, no complex numbers. That simplifies things. Second, instead of these constants A1 and A2, you need to find these constants C1 and C2. So let's use this form of general solution and find the particular solution for these initial conditions. I will set the initial position to be 2 and the initial velocity to be 0. The first initial condition will give me this. This is the general solution at time 0, which simplifies to this, and that is supposed to be 2. So from the first initial condition, I will get that the constant C1 is 2. From the second initial condition, I get this. This is the derivative of the general solution. I need to evaluate it at time 0, which I have done here. Here I have also used that I already know that C1 is 2. When I evaluate this, I get that C2 is 2/3. So the two initial conditions gave me the constants C1 and C2, which I can substitute to the general solution, and that will give me this particular solution. This is how my ball will move when its initial position is 2 and its initial velocity is 0. You can see the position of the ball is given as a sum of a sine and a cosine, the amplitude of which is exponentially damped. Here I have it plotted. You can see that the position of the ball will come to rest at 0, but it will come there in this rocking oscillatory fashion. When the spring is strong and the friction is low, then the ball does not come to rest evenly as in the previous case, but it overshoots, then it overshoots again, and it will come to rest in this rocking or oscillatory fashion. It is worth noting that these oscillations, that is, these sines and cosines, are present because we have these complex exponentials here. And we have these complex exponentials because the roots of the characteristic equation are complex, which we have because the discriminant of the characteristic equation is negative. Note that in the previous case, the discriminant was positive. The roots of the characteristic equation were real, so the solution was given by the sum of real exponentials, and there were no oscillations. Here we have complex roots, so we have oscillations. Now let's take a look at two remaining cases. Here I have the same setup as before, but I have moved to an ideal world where I have no friction. My coefficient of friction is 0. In this case, the characteristic equation will be this, and when you solve this, you will get two complex conjugate roots. This case is actually quite similar to the previous one, but the difference is that now these roots are purely imaginary and they have 0 real part. In the previous case, the real part was non-zero. This sigma was non-zero. Now, sigma is 0, so the general solution simplifies into this. But the rest is pretty much the same. Let's say my initial conditions are the same as in the previous case, that is, my initial position is 2 and my initial velocity is 0. I can use these conditions to find the coefficients C1 and C2, which turn out to be 2 and 0. Then I substitute these values into my general solution and I get this particular solution. So for these initial conditions, my ball will move like this. Here I have it plotted. And you can see that if you live in a frictionless world, your ball will oscillate with undamped oscillations indefinitely. Now the last case. This is a special case that requires a special change in the general solution. Let's say that I have these constants, in which case my characteristic equation is this. This equation has 0 discriminant and consequently a single root. But because mathematicians insist that a second order polynomial has 2 roots, we say that this is a double root. If you have one double root, you can run into trouble if you write your general solution like this. This is a solution of your differential equation, but it turns out that this does not give you all the solution of the differential equation. In this special case, where you have a single double root, your general solution has this form. It is composed of 2 exponentials, both of them have the same lambda, but the second exponential is multiplied by t. So remember, if you get a single double root of the characteristic equation, this is a general solution that you need to use. The computation of the particular solution is the same as in the previous case. Somebody needs to specify the initial conditions, and you need to find these constants from those conditions. Okay, on the previous slides I showed you an example of a second order system and I illustrated the different types of behavior a second order system can manifest. Now let's write this down in a general form. A general homogeneous second order differential equation with constant coefficients looks like this. To get a specific behavior of your second order system, you need to provide two initial conditions. Typically, we provide the value of your function and the value of the derivative of your function at some time. You can start looking for the solution of the differential equation in this form. You substitute this form into your differential equation, evaluate the derivatives, cancel out the a's and the exponentials, and what you are left with is the characteristic equation. This is a second order polynomial which will have two roots, lambda 1 and lambda 2. Now the solution will depend on what types of roots you get. If the discriminant of your characteristic equation is positive, you get two real roots, in which case the general solution will have this form. These coefficients a1 and a2 you can find from the initial conditions. So the response of your system will be given by the sum of two real exponentials, and you can essentially get two types of behavior. The first type you get when both roots are negative. In this case, you have two exponentials that go to zero with increasing time. So the response of your system will asymptotically approach zero. This type of behavior we call stable overdamped. The next type of behavior you get if either of these lambdas or both of them are positive. In that case, at least one of these exponentials will be increasing to infinity or decreasing to minus infinity. Consequently, the response of your system will not stabilize at some value, but it will be ever increasing or ever decreasing. This type of behavior we call unstable. If the discriminant of your characteristic equation is negative, you get two complex conjugate roots. Here you can still use this form of the general solution, but it is usually more convenient to use this form. These two forms are equivalent. The second one is just easier to work with. Again, either these constants or these constants you will get from the initial conditions. The response of your system will actually depend on the real part of your roots. If the real part of your roots is negative, this exponential will be decreasing and you get behavior like this. This system will stabilize at zero, but it will approach the stable position with this rocking oscillatory motion that comes from this sine and cosine. This type of behavior we call stable, as in this case, but to distinguish it from this case we call it underdamped. Now if the real part of your roots is positive, this exponential will be increasing and you will get a behavior like this one. Here the system will not stabilize, therefore we call this behavior unstable. A case on the margin between these two cases is when the real part of your roots is zero. In this case, this exponential is equal to 1 and the amplitude of the sine and cosine remains constant, which will give you this type of behavior. This type of behavior we call marginally stable and undamped. Now, this behavior you get if the discriminant of your characteristic equation is positive. This behavior you get if the discriminant of your characteristic equation is negative. This is the marginal case in between these two when the discriminant is zero. In this case, you get a single double root and your general solution looks like this. Here the second exponential is multiplied by t. As before, these constants you will get from the initial conditions. The behavior of your system will again depend on the value of this double root. If it is negative, with rising time these exponentials will come to zero and your system will asymptotically approach zero and stabilize. This type of behavior we call stable, critically damped. Now, if lambda was positive, these exponentials would be rising to infinity and your system would become unstable. I have not drawn this case here, but I hope you can imagine it. Okay, now what are these plots with crosses in them? These plots show where the roots of the characteristic equation fall in the complex plane. In this case, your roots are real negative, so they fall on the left half of the real axis of the complex plane. In this case, the roots are still real, but at least one of them is positive, so at least one of them will fall on the right side of the real axis in the complex plane. In this case, the roots are complex and their real part is negative, so they fall on the left-hand side of the complex plane. In this case, the roots are complex, but their real part is positive, so they fall on the right-hand side of the complex plane. In this case, the real part is 0, so the roots are right on the imaginary axis. And last, in this case, we get one double root which sits on the real axis. If the system is stable, the double root is negative, so it will sit on the left-hand side of the complex plane. If the system was unstable, the root would be positive and the root would sit on the right-hand side of the complex plane. Now there is a common pattern in all of these plots. Note that you always get stable behavior if the roots of the characteristic equation are on the left-hand side of the complex plane, and you always get unstable behavior if the roots are on the right-hand side of the complex plane. If your roots are right in the middle on the imaginary axis, you get marginal stability. It actually all comes down to these exponentials, these exponentials, these exponentials. If the real part of the lambdas, that is the real part of the roots of the characteristic equation, is negative, all these exponentials will asymptotically approach 0 with rising time and you get a stable system. If the real part of lambdas is positive, these exponentials will go to infinity and you get an unstable system. So to judge the stability of your system, all you need to do is to get the roots of your characteristic equation. If their real part is negative, they fall on the left-hand side of the complex plane and the system is stable. If their real part is positive, they fall on the right-hand side of the complex plane and the system is unstable. If the roots fall on the imaginary axis, the system is marginally stable. There are still things left to be said about this damping I keep mentioning. I could explain better why we use these terms underdamped, overdamped and critically damped, but I will leave that for the beginning of the next lecture. Now, instead of further math, I will show you a practical example where you will be able to see these different types of behavior. The practical example will be the inverse pendulum I showed you on the first lecture. Just a reminder, this is what we call a pendulum. If I turn this pendulum upside down, it will become an inverse pendulum. And not surprisingly, the inverse pendulum is not going to be stable in this upright position, unless you put a step motor on the bottom and the regulator on the top, in which case you can actually make this inverse pendulum stable. Now, when you make a couple of approximations and simplifications, you can approximately describe the movement of this pendulum using this differential equation. This x of t is the position of the top of the pendulum, and the x sub b of t is the position of the bottom of the pendulum. And these are just some constants. If the bottom of the pendulum is fixed, this is an unstable system, which corresponds to the fact that the pendulum without any regulator is going to fall. But you can add a regulator like this one. You can control the position of the bottom of the pendulum, that is, you can control that stepper motor on the bottom of the pendulum using this formula. The position of the bottom will be given as some constant k1 times the position of the top of the pendulum plus some constant k2 times the derivative of the position of the top of the pendulum. When you substitute this equation into this one, you will actually still get a second order system, but now using these constants k1 and k2, you can change the properties of the system. You can change the position of the roots of the system. Currently, I have set constants k1 and k2 to 1.1 and 0.1. In this plot, I have plotted the position of the roots of the characteristic equation of my system for the values of these k1 and k2. You can see that this setup gives me two real negative roots, so my pendulum should have stable overdamped response. So let's check that. If I move the pendulum from its zero position and then let it go, it will come to its original position without any oscillations. Now I have a wireless link to my pendulum, so I'm able to change these constants in real time. Just to demonstrate the wireless link, I can move the pendulum back and forth like this. But that was just for show. Let's take a look at what happens when I really change these constants so that my system will have two complex roots. Now the response of my system should be stable but underdamped. When I move the pendulum and let it go, it will come back to the stable position, but before stabilizing, it will overshoot a couple of times. If I design a regulator for the inverse pendulum, this is probably not what I want. Now I have reset the constants k1 and k2 to their original value. And let's see what happens if I change these constants so that one of the poles will move to the right hand side of the complex plane. Now I have one pole on the right hand side, and you can see that the pendulum behaved like this. It just exponentially ran away to one side. Now I have my pendulum stable again, and let's see what happens if I make the roots complex and then move them to the right hand side. The pendulum again becomes unstable, but this time we had this kind of response. So this is how the position of the roots of the characteristic equation corresponds to different types of behavior of your system. You can see that when you design a control system, it is crucial to understand what your system does with different positions of the roots of the characteristic equation.